Okay, this lesson is unrelated to everything else we're doing in the unit. However, it's a very key lesson for transitioning from learning new material to reviewing, okay? Because the first thing we ever did in this class was limits. So I guarantee you, you forgot all of the algebraic techniques that we use to find limits. So you're going to enjoy this lesson because of that reason, okay? Now, let's remember how we tackled limits. We want to see what a function is approaching as an x value is getting very, very close to a certain value. Our first attempt is to find potentially if this expression can be evaluated at the function value. So does this expression produce a function value, a y value, for an x value of 3? So I plug in 3, and turns out I get 0 over 0. Now, that could mean a couple things. It could mean that when x approaches 3, or when at 3, this function has a hole where it would have a limit because the function values would be approaching the hole from the left and the right, or it could have an asymptote, or it could be something else, but typically it's a hole or asymptote. Okay? And the way we kind of tackled it is by factoring this and simplifying it. We can essentially remove the hole, the removable discontinuity, and we have a simpler function that does not have a hole, but has the same exact y values everywhere else as this expression that we can plug 3 into to find that the limit is 6, right? And that I would expect you to do once we start reviewing, okay? But let's look at these two. Do we need this for another second? Let's look at these two. Both of these can be evaluated algebraically. But I bet most of you right now would just kind of shrug your shoulders and be like, nope, can't do it. Am I right? All right. Well, you can factor this. This is a difference of squares like the other one. This is e to the x plus 1 times e to the x minus 1 divided by e to the x minus 1. Okay, and of course the first thing I attempted is to plug 0 in, and I get 1 minus 1 over 1 minus 1, that's 0 over 0, so I can't do that, which is why I have to factor. Those cancel, I plug in 0, I get 2. Okay? Now, what about this one? I plug in 0, I get root 4 minus 2 over 0, that's 0 over 0, so that doesn't work. Who is shrugging your shoulders right now? Who is confident that remember the algebraic tool we can use to figure out this limit? Ms. Klein? Hey, stab at the dark. It's okay. Can't help us there, but good stab. Yes. It's a C word. The conjugate is correct. Good. Now, obviously, most of you are shrugging your shoulders right now, but we would have to do this. This is a technique that we did. Okay, I'm going to do it really quickly. We'd end up with just negative x over x times root 4 minus x plus 2, and these would cancel, providing us a simpler function that we can plug 0 into. I'd have negative 1 over root 4 plus 2, which is negative 1/4. Okay, and that's just multiplying by the conjugate. I might as well show you actually the step. This becomes positive 4 minus x plus, minus 4. The 4s would cancel, right? Multiply by a conjugate, you'd have a squared minus b squared because the middle terms would cancel. Okay, so that's why I got negative x right here. Okay, good. So a lot of shrugged shoulders. Now, this one is easy to do if you know how to do it. But it's impossible. There's no algebraic manipulations that you can do if you don't know how to do it. We did these actually not too long ago in Unit 6. You have to remember the definition of a derivative, right? This is essentially asking us, what is the derivative of the sine of x when x equals pi over 3? Yes. Good times. Okay, so a lot of you were just like, don't know how to do that if you saw it. It's the weird non-shortcut where we had to algebraically distribute things or find common denominators, all that stuff. When we first learned derivatives, we used this magical formula that we turned out was not very magical. The only questions you see with the definition of derivative are limit questions like this. Typically, they'll give you a multiple choice question like this, and they say evaluate this limit, and you just have to understand that that is the recognition of the definition of a derivative. Find the derivative at the correct point. Okay, that's 1/2. Okay, now there are certain limits that are impossible to do. There is no algebraic manipulation that you can do to figure out this limit. It's just you get 0 over 0 and you're stuck. Okay, so I will give you another technique to help you not have to shrug your shoulders when you see these limits, okay, once we start reviewing. And it starts with this. Let's look at this limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. Let's, in our calculators, graph these two equations. Graph the numerator and graph your denominator, and then zoom in around the point 0, 0 that they both have. Okay, so go ahead and do that. Here they are with a standard window. Zoom in 4 times around 0, 0. And talk with the neighbor about what you see and make sure you see the same thing that they're seeing. So zoom in, enter, zoom in, enter, zoom in, enter, zoom in, enter. There's,
It's not exactly 0, 0.
it is exactly 0, 0.
Wait, what? I mean, I didn't zoom it. Oh.
You did the same thing. Let's make sure we're typing in our equations correctly. It's e to the x minus 1, not in the power. Okay? All right. Compare your graphs with a neighbor after you zoomed in 4 times and talk about it.
What is it supposed to look like
When you zoom in? Oh, zoom, 2, enter. Yeah. You got to press enter to tell the calculator where to zoom in. Press on. All right. So what do we see? 2 lines, right? Now, this is a very key concept in calculus, the so-called linearization of any curve if you zoom in enough. This is why we use tangent lines to approximate function values. Because if we zoom in close enough, and as long as we're dealing with values really, really close to a certain location, a line can be used to essentially approximate or give us almost the exact value, which is approximating, at a certain location. Okay, so that's important. Well, how is that going to help us? Yeah, instead of working with e to the 2x minus 1 and e to the x minus 1 as x approaches 0, knowing that as x approaches 0, if we look really close to the locations at 0, this looks like a line, and this looks like a line. Why don't we just use lines instead of the function? Well, now the question is, how do we find the equations of those lines at those locations? I need two things for a line. We all know this. We need a point and a slope. What's the point that both of these lines share, thankfully? 0, 0. Well, that's easy. Now, it's always going to be that for all these equations, but typically we'll be using situations where the y-coordinate is 0. But how do I find the slope of those lines that I saw on my graph? Guess? My goodness. Mr. Noe, you are correct. So let's zoom out. Let's go back to Zoom Standard. What line would we be able to see from out here right at that location 0, 0? No. I'm thinking of more of a concept. Yes, the derivative. The tangent line. If I drew a tangent line right here and right here, well, zoomed in, those would be the tangent lines. So those slopes would be the tangent slopes after we zoomed in, right? So how do I find those slopes? Take the derivative. So let's find the derivative of e to the 2x minus 1 when x is 0. Let's find the derivative of e to the x minus 1 when x is 0. Remember your chain rule, it's e to the 2x times 2. You plug in 0, we get 2. So the slope of that line that we saw was 2. The slope of this line, that would be e to the x when x is 0, that would be 1. Giving you two equations. Y minus, let me just move this down. Y minus 0 equals 2 times x minus 0. And y minus 0 equals 1x minus 0. Well, that's just y equals 2x and y equals 1x. Why don't we just use those equations as x approaches 0, because those equations essentially are these functions at 0. Well, this is easier to simplify, and this is easier to find. I can factor out the x's, they cancel, and I just get my limit. Okay? That's a lot easier than remembering how to factor e to the 2x minus 1. Well, this concept could be used for any limit at any location. I could take like x squared over 4x minus 1 and find the limit as x approaches 2 by turning this into a line. Would I want to, though? Why wouldn't I want to? Because I can just plug this in, because this expression has a function value at 2. So I can just plug this in, and I don't have to turn this x squared into a line. Or, you know, if this was an x squared as well, maybe if this was e to the x plus 1, you know? Yes, I could turn these into lines right around 2, and I could use those lines to help me find the limit, but that'd be easier, right? Well, the concept, however, is super helpful for this. It'll be super helpful for certain situations. And the whole linearization concept is used, however, there's a guy called L'Hopital who kind of looked into this linearization concept a little bit closer and discovered something. It's the same concept, but it's not the same application, okay? L'Hopital says if a limit, that's how you say it, L'Hopital, if a limit of some function, maybe expressed by a quotient, is equal to 0 over 0, or f of a minus over g of a is 0 over 0, or it's infinity over infinity, then turns out you don't have to look at just the equations of the lines. You can just look at the slopes of the tangents. And if you find the slopes of the tangents at the specific location, that is going to be the same as your limit algebraically, or your limit of your expression here. So it's almost like going a little bit further and said, if we can't find the limits because we can't find the function value, you can find the slopes of the tangents, which is the linearization concept. And then those are just going to be your answers. Just like the slopes of the tangents for our one example we did were just 2 and 1. So we would express that this equals the derivative at a over, I can go one step further before we go there, equals the limit as x approaches a of the derivative of x over the derivative of g, which sometimes will equal f prime of a over g prime of a. Sometimes we'd have to, simplify that. And this goes further. We could also say that's equal to the limit as x approaches a of the second derivative of x over the second derivative of g. And you could keep going. You could keep taking derivatives and finding slopes of tangents or slopes of tangents, and that'll help you find your limits. Okay? This is L'Hopital's rule, and this is a big if. Okay? We don't want to use L'Hopital's rule because it won't work for certain equations, expressions like this one. It won't work. Okay? It's only a specific situation when our limit is indeterminate because it's 0 over 0 or infinity over infinity. Okay? Because if it has this, we would just go here. Okay, so let's go back and do the previous examples. And instead of doing them algebraically, we can use this new rule. First, I noticed that this is 0 over 0 if I plug 3 in. So it's indeterminate. So the L'Hopital's rule can apply. All I would do is take the derivative of the top and the derivative of the bottom and find that new limit at those locations, or find the slopes of the tangents of the functions at 3. This is 6 over 1, which is 6. Easy to find, and it's the same exact answer that I found using algebra. Let's do the next one. We found that this limit was equal to 2. Well, instead, knowing that this is going to be 0 over 0 if I plug things in, I can take the derivative of the top and the derivative of the bottom, giving me e to the 2x, don't forget the chain rule, times 2 over e to the x, find that limit as x approaches 0, and I get 2 over 1, which is 2. Same as what I found when I turned these into equations of lines, and I had 2x over 1x. Same as I found if I used algebra to factor this. Okay? So, helping. This conjugate problem, maybe we forgot how to multiply by the conjugate. Well, knowing that this limit, thankfully, is indeterminate, you can use L'Hopital's rule. And maybe the mistake that we will make, though, is the incorrect derivative of that. Why don't we go ahead and all do this one by taking the derivative of the top and the bottom and find out the limit as x approaches 0 of those derivatives. We all need to remember the chain rule. And we all need to remember that the derivative of minus 2 is just 0. It's just minus 0. Integral. Now is when we start getting all tripped up because I forgot my derivative rules and I'm mixing up my derivative rules with my antiderivative rules. Remember, move the power down first. Subtract 1 from your power second. Okay, you should get the same answer that we got above when we factored, when we multiplied by the conjugate. Okay, so that's an easy way to check. I keep doing this. Oops. Oh my goodness. I know. It's funny. I always do that. I always say, watch out for this, and then I do that exact same mistake. Okay, I need that -1 there. Why? Because of the chain rule, because I need to take the derivative of the inside, which is 4 minus x. The derivative of minus x is -1. Okay, which is why I have -1/4. -1/4, same answer that I found by multiplying by the conjugate. However, maybe easier to do. Okay? Same deal here. Now this actually is done the same way as you would do this normally, which is you would take the derivative of the sign at x over 3. But if you look at it here, and what people make mistakes on with this is they take the derivative of sine pi over 3 and they tell me it's cosine of pi over 3. But we know that's not right because the sine of pi over 3 is just a number. The derivative of a number is 0. So this would just give you cosine of pi over 3 plus x over 1. Find the limit as x approaches 0. You just get the cosine of pi over 3, which is 1/2. Okay? Well, now we come to this impossible one. We can finally find this impossible, algebraically impossible limit by taking the derivative of the top and the bottom and finding its limit as x approaches 0. Okay. Now, this also can help us for limits at infinity. If we have infinity over infinity, we can use L'Hopital's rule. I will tell you, though, that it's not super helpful. I would rather you recall the rules for limits at infinity. So we will get to one if we are unsure of things that we can use L'Hopital's rule for. Let's recall some rules for limits at infinity. So think about it. I'm plugging in larger and larger values for x into our numerator and our denominator. Who remembers what I can almost not have to worry about when I'm plugging in larger and larger values of x into this expression? Beautiful. I heard it from a lot of you. Everything after the largest power. Because as we plug in bigger and bigger values for x, this will dominate what is going on in my numerator. And that 2 times the large value plus the 1 will end up being like adding a very, very small decimal point to a very, very large number. Okay? This won't matter, and this won't matter. The 1 won't matter. So really, we just have to compare x to the 10th to e to the x. Now this, you have to remember that when we have a a variable in an exponent, we will always go faster than x to any power, and that this would essentially be like some number divided by infinity, which is 0. I'd rather you remember that than use L'Hopital's for that. Same for this. Remember that the log function grows exponentially slowly, since it is the inverse of e to the x, which grows exponentially quickly. This is the slowest growing function. So we would have essentially a huge number divided by just a smaller number, creating a larger and larger number, essentially. This, we remember that the 5,000 won't matter. The 9x and the 1 we can disregard, and if we want to take the limit as x approaches infinity of this entire thing, it's the same as just this expression. You can cancel the x squareds, you get 3/2. Now, all of these we could have used L'Hopital's rule for, but I'll show you that you'd have to just continue to take the derivatives and you would be able to get the answer this way quicker. But something like this, if we are unsure about the growth of things, L'Hopital's rule will work. We have the log of x to the 4th over x cubed. Now you see the log function and you're like, okay, that grows slowly, but we have x to the 4th, that's a larger power than x to the 3rd. Maybe you're not sure. Well, what you can do is take the derivative of the top and the bottom and evaluate that limit. Now, what's the derivative of log of x to the 4th? Good, very good. 1 over whatever we have times the derivative of what we have. This simplifies to just be 4 over x over 3x squared, which is the same as 4 over 3x cubed. You can find the limit as x approaches infinity and understand that, yes, x cubed is going to grow faster than the log of x to the 4th. This will be approaching 0. Okay, now, those are going to help you for certain limits. There are some questions on the AP exam, the BC exam for all you BC exam takers, that you have to know L'Hopital's rule for, and you can't use algebraic methods like we did up here. Here's an example of one. Okay, this is an AP question from a previous year. Let's do this question. Ready, set, go. My first attempt would be to plug in 2, but I realize I get 0 over 0. That should give you a big hint as to how you would tackle this. Get your answer, compare it with a neighbor. A, B, C, D, or E. Next year, not you guys, there's only going to be A, B, C, and D as your possible answers. You guys get E. And next year, they say, though I'm not sure if it's going to be true, that they won't have like the opposites of the correct answers. So they won't have, those trick answers that if you do one mistake, you get your answer and you're like, sweet, I got the answer. You circle it, but that's the wrong answer because you make a mistake. They said that they're not going to do that anymore.
Now they're just going to do like right.
I don't know. I think that's the beauty of the AP test, is that they put those answers in there, and it makes it hard.
But then you can just like keep going until you get one of the answers.
I know. Okay, get this answer. What do we get? Check your answers with a neighbor. I don't see everybody checking.
you just use 0 for the top, or?
If you get this, that means this limit is indeterminate. That means you need to use L'Hopital's rule. Take the derivative of the top and the derivative of the bottom, and then find that limit at 0. I don't know. I didn't do it.
Yeah, so you do double and double
Okay, so I take the derivative, I plug in 0, I plug in 2, I get f prime of 2, which is 0 again, and then I get 0 again. It's like, oh man. Well, remember, you can just keep taking derivatives. You can go to the second derivative, you can go to the third derivative. Here it is. There's the second derivative. There's the third derivative. So let's take the derivative again. A lot of your quiz questions will be like this. This is just 2x minus 2. The derivative of 2x minus 4 is just going to be 2. F double prime of 2 is 5. 5 halves is the answer B. Okay? All right, your homework's out of the book. Tomorrow. Tomorrow at 4, at like 5 or something. There should be no thought. Let me pause.